Okay, so formally then we say that, okay, so let me just make sure we're clear on the idea of an inclusion function just before I carry on, because I want to talk about this inclusion lemma, which basically has to do with particular kinds of monics which occur in this category set to the power of c. So the idea then is that if we have a subset y of a set z, then there's going to be an inclusion function I from y to z, and it basically just works so that it maps every element little y of capital Y to itself, but considered within this larger set z. Okay, so that's the idea. Now, this next thing is this inclusion lemma. So this is really sort of illustrated in a way by this picture here. Okay, let me just change that into an A there. And you see this M here that we've got represented. I can just rub this stuff out now. This M that we've got represented here, we can really think of it as just sort of corresponding to selecting a subset of the vertices of capital A and a subset. So, I mean, what have we got going on in this picture? We have a monomorphism M from X to A. But you can see by the way that this is drawn that essentially this monomorphism is really just sort of selecting a subset of the vertex set of A, and in this case 1 and 2, and it's also selecting a subset of the loop set of A, just this loop little a in this case. Okay. And the basic idea is that it's always possible to build these special kinds of so-called inclusion monics where we literally just pick a subset of the vertices of A and a subset of the loops of A. Now, those subsets have to have a special feature. They have to be closed under the S action. Okay, so in this context of this category of functions, that means when we find a vertex of a loop, if that loop is in our chosen subsets, then the vertex also should be in our chosen substructure. Okay. So this is the idea, and if as long as we can, whenever we select these kind of subsets, so in this case here, we'd be selecting this subset 1 and 2 of the set of vertices 1, 2, 3. So the set of vertices is called A of V, and we select this subset of the vertices that actually in the lemma I'm about to explain, we denote this as A subscript V. We also do a similar thing with the loops. In this case here, we're selecting just this loop A, but we're doing that out of the set of all loops, which is consisting of A, B, and C. So A, B, and C together are forming this set of loops of capital A, which we call A of E. And then we denote A subscript E to be our selected sort of loop in our sort of selected subset. And you notice that this monic is really picking out this A of V and A of E here. So in a way, we could think of, well, the vertices in this subobject M are 1 and 2. The edge in this subobject M is A, okay? But really, in a sort of set theory-centric point of view, we'd say, well, we're selecting there's a subset A subscript V of A of V, and as a subset, A subscript E of A of E. And also the important thing here is that they're closed under the S action. Okay, so when we find what is the vertex of this loop A, well, essentially we're doing A of S on that little a here. So we're applying this function A of S. And notice that we're getting another thing in one of our selected subsets. We're getting a member of A subscript V. We're not going to 3, which is outside of our chosen subset. We're getting something in A subscript V. So this selection of A of V, this subset, and also A of E, this kind of collection of subsets, is itself forming a proper kind of sub-object because it's closed under the S action. Remember, when we want to find a vertex to a loop, that better give us something that's in our substructure as well. Otherwise, our substructure is not itself a proper object. Okay, but this is. That's why we can form this object X, which is a properly defined object, because the loop which is present in our sort of subsets, its vertex is also present. So the sort of selection of these subsets, A subscript V and A subscript E, is closed under this S action. And what the first inclusion lemma basically says is that when you pick your kind of if this is for general set to the power of C, not necessarily for category of functions, it says that if you can pick these kind of subsets of E figures for every object E in the category C in such a way that that collection of subsets is closed under the S action, then that's always going to correspond to one of these kind of inclusion monics. Why do I call them inclusion monics? Well, because we essentially form this object X out of these kind of subsets of E-type figures of A, and then we just think of the kind of mapping, the kind of actual monomorphism arrow. Each of its components are then just inclusion functions, just like this one here is just like, for example, the vertex component of this monomorphism here is just sort of including these vertices 1 and 2 within this larger set of vertices 1, 2, and 3 of this object A. Okay, so that's the basic rundown of this inclusion lemma 1. Now this is the formal statement of it. For an object, so this is in general for set to the power of C, it says that for an object A of set to the power of C, suppose we select a subset A subscript E of A of E for every object E in the category C. And now suppose that for any arrow S from E to V in the category C, we have that A of S sends each element of A of E, sends each element of A subscript E to an element of A subscript V. Okay, so basically what I'm saying with this sentence here is that this sort of collection of subsets here of the E-type figures is a collection that's kind of closed under the S action. Okay, so it's the idea is again illustrated up here, where for object E of category C, we select E subscript E. That's this thing here. We also select A subscript V, a subset of A of V. But we suppose that all this collection of subsets is such that for any S, we have that A of S always sends the elements in A subscript E to elements of A subscript V. We don't have stuff in this where we do an S action and we get something outside of one of our selected subsets, because we want these selected subsets to be basically forming the kind of E figures of another object, an object X. Okay, so we can form this object X, which has A, which has its E figures as A subscript E, and its V figures as A subscript V, etc. And then the way that the S action is defined on X is just the same as the way that the S action is defined on A, but just restricted to these chosen subsets. And that works properly because we've assumed that the S action always sends members of these selected subsets to one another. So this is the idea. Now let's go through this formally. So, okay, we suppose we have this collection of subsets. We have a subset of A of E called A subscript E for every object E. And we suppose that the collection of subsets is closed under the S action. And then what we do is we form another object X of our category. Okay? And this is sort of like what I'm picturing up here. The idea is that we set X of E to be A subscript E, this subset, for every object E of our category C. And then the S action with this object X is defined as follows. For any arrow S from E to V, we have that for any arrow S from E to V, we have that this function X of S is just defined to be the restriction of A of S to this subset A subscript E. So it's the source of A. So the source of X of S is A subscript E equals X of E, and the target of X of S is A subscript V equals X of V. And the way that X of S is defined is just the way that A of S is defined, but only on these elements. So the way that X of S is defined is just the same way that A of S is defined, but it's just we're only interested in how this function works on members of this kind of subset, A subscript E. And as I've said, all the values that A of S takes are going to be in A subscript V. We're assuming that. So we can really think of X of S as a kind of function from A subscript E to A subscript V, or equivalently from X of E to X of V. Okay, so we do all that. And then the basic claim is that if we do that, X is going to be an object of our category. Okay. And more than this, it's not just an object, but it comes equipped with a sort of monomorphism I from X to A. Okay, and this is really what we call the inclusion monic. So the way I say it, I'm trying to do it formally. So I say that there's a natural transformation I from X to A. Now, the ETH component of this arrow I subscript E, is just going to be an inclusion function. Okay, it's just going to be including X of E into A of E, because X of E really looks like a subset of A of E. And the claim then is that actually I itself is not only a natural transformation, it's not only an arrow of set to the power of C, but it's actually a monomorphism of set to the power of C. And we call such a monomorphism an inclusion monic. Okay, so this is basically a special kind of monomorphism where it doesn't really alter the kind of names of the elements. It's like a monomorphism from a part of a structure where everything in that part is named the same thing as it is in the kind of full structure, and the kind of mappings are just essentially regarding that stuff in the substructure as part of a larger structure. It's just sending the same named element to itself, but in a larger structure. Okay. Now, is every monomorphism a inclusion monic? Well, no. So here's a picture. Here's a monomorphism M into A, and this is obviously not an inclusion monic because you see it's sending this vertex is called 1 dash and it's getting sent to 1. This loop is called Q and it's getting sent to A. So M here is not an inclusion monic. The components here are not inclusion functions, okay? But in fact, this monomorphism M is equivalent to a inclusion monic, because if we just relabel the vertices and loops of this bouquet here, we can call, instead of 1 dash, we'll call it 1. Instead of 2 dash, we'll call this 2. Instead of Q, we'll call this A. And now look at this monomorphism I. This is an inclusion monic, and it's equivalent to this other one. It's basically just the same, but we're relabeling the kind of vertices and loops. So this is the basic idea. And so this is the basic idea. And our second inclusion lemma basically says that it's always possible to do this kind of thing in general. Okay, if we have any monomorphism M in set to the power of C, it's always possible to find one of these inclusion monics which is equivalent to it. Okay, so that's our second inclusion lemma. So inclusion lemma 2, every monomorphism in set to the power of C is equivalent to an inclusion monic. And when two monomorphisms are equivalent, I mean, they're basically the same as far as we'd be interested in from a kind of arrow-centric point of view. Okay, they have exactly the same arrows in them. So this is very useful for us because it allows us to, if we like, always take this kind of set theoretic view of what these monomorphisms are, what these sub-objects are, okay, if we want to. So there we have it. Now, the third result Okay, so now then the third result that I want to talk about is this thing I call the membership lemma. Okay, now the basic idea here is that say we want to work out, so say we have an arrow H into A, and we also have this sub-object M of A, and we want to know, is H in M? So one way to say it, we can just say, well, you know, does there exist a K such that H is equal to M after K? And, you know, maybe we can find such a thing and we'd be okay, but we'd really like to have a sort of more finite kind of idea for, you know, when we could check if H is really in M. So, I mean, in general, in a category, we do have this theorem which says that H is going to be in M if and only if for any alpha which goes into the source of H, we have that H of alpha is in M. Okay, so this is for all alpha. Now you could say, okay, that makes this problem a lot worse. So we have to think about even more arrows. Well, maybe so, but in the category of sets, it's a bit simpler. It turns out in the category of sets, this isn't really too important for our current thing, but it illustrates the idea. We have this result that for every we have this result that H is in M if for every object we have this result that H is in M if and only if for every arrow alpha from the terminal object to the source of H, we have that H after alpha is in M. And this is actually a really cool result because this is essentially saying that and this is actually a really cool result because it's essentially saying that when we're working in the category of sets, we know that a function is going to be in a particular sub-object, as in this function H is in this sub-object M, if and only if H sends every kind of point alpha into this kind of sub-object M. Okay, so it's essentially saying that in this category of sets, when we say a function is in a particular sub-object, we're essentially saying that all the values of that function are, or that everything in that function's sending all its values into that sort of corresponding subset. Okay. Now it turns out we have a kind of analogous result in set to the power of C. It's just that we're not just looking at the elements of a set when we're thinking in set to the power of C. We have these structured sets. They have different kinds of figures, E figures, V figures, and so on. And our sort of corresponding result is that one of these maps in set to the power of C is going to be in a particular sub-object precisely when it's sending all the kind of E figures into that substructure, it's sending all the V figures into that substructure, and so on. And that's basically what the membership lemma says. So I'm just going to read it through again, and then we'll actually we'll have a quick look at some sort of practical example. In all honesty, some of these results are rather abstract, and I encourage you to go through the proofs if you really want to sort of have a full understanding of them. Anyway, basically what this membership lemma is saying then is, suppose we have a subobject M of A, as in a monomorphism from X to A, and suppose we have an arrow H from capital H to A. Now, what the result says is that H is going to be in M if and only if, for every object E of our category C, we have that for every theta in H of E, in other words, for every E-type element of H, theta, we have the H after the kind of arrow corresponding to theta under the Oneida correspondence. In other words, I'm talking about H after, we have the H after theta under arrow, where theta under arrow is this kind of, we have that H after theta under arrow is in M. And here, theta under arrow is just this kind of arrow from hom E comma blank, which sort of corresponds to this element theta of H of E. So what is this result saying? Well, essentially what it's basically saying is that an equivalent way to say that H is in M is to say that H is sending all of the kind of E figures, is that H is sending all of the kind of E figures of its kind of source objects into M, okay? Because when we write H after theta under arrow, that's a kind of composition, but it's essentially a composition. It's an arrow, but it's an arrow from a Hom functor, which basically just corresponds to kind of like how H is acting on that E figure theta. Okay, so let's have a look at this with an example so we can see it more clearly. So let's say we have this kind of green arrow H here, which is a map from capital H to A. And we also have this sub-object M of A. In other words, we have this monomorphism M, which is coming into A. Now we're interested in, is H in M? And basically what this result's saying is that an equivalent way to say that H is in M is just to say that is just to sort of think of M as kind of selecting this sort of subset of the vertex set of A and selecting a subset of the loop set of A, and then notice that all of the kind of values of stuff that, you know, H sends things to are all taking place inside those sort of chosen subsets. Okay, but more formally, what we're basically saying is that for every sort of E-type element, or in this example, V-type element, for every such thing theta of H, we have that such a thing is always mapped by little h into something in these selected subsets. But another way to say that, the kind of more formal way, is that if we have such a theta, such a V-type element of H, well, we can always form this sort of arrow theta underline theta, so we can always form this sort of corresponding arrow theta under arrow via the Oneida correspondence. And this results essentially saying that what we want is that H after theta under arrow, which is essentially going to be like the kind of arrow from Hom V comma blank into A, which is really just sort of corresponding to this sort of element where theta got mapped to. We want that to be in M. Okay, so basically the result is saying that H is in M if and only if H after theta under arrow is in M for all theta under arrow, sorry, for all theta in, which is a sort of V-type element of the source of H, and for all V, okay? Now, maybe an easier way to understand this is to there's another equivalent way to say it. If and so another way to say it is that if and only if HV of theta is in X of V, for all theta in H of V, for all V, okay? Now, this isn't actually part of the statement of that membership lemma, but it's a kind of nice intermediate stage. Now, I'm talking about X here. What am I talking about X for? Well, here we're thinking of X as the kind of inclusion monic, which is equivalent to M. Okay, so what I'm basically saying is that an equivalent way to say that H is in M is to kind of find the inclusion monic, which it's equivalent to, and then that's really giving us a load of subsets, so a subset of the loops, a subset of the vertices, and so on. And if we're sure that H here is sending everything into those subsets, that's an equivalent way to say that H is in M. Okay, but then the kind of arrow-centric way to say it is really this, which is the actual content of our membership lemma.